In 1736, a man looked at 7 bridges and invented an entire branch of mathematics. Then he went blind. And somehow got more productive. This is the story of Leonhard Euler, the most prolific mathematician who ever lived, and how a single career reshaped the entire landscape of human thought. Konigsberg, Prussia. A city built across a river, with 2 islands and 7 bridges connecting them. The locals had a puzzle. Can you walk through the city, crossing each bridge exactly once, and return to where you started? People tried for years. Nobody could do it. Euler didn't try to walk the bridges. He asked a different question entirely. He stripped away the geography, the river, the cobblestones, and reduced the problem to dots and lines. 4 dots for the landmasses. 7 lines for the bridges. And then he proved, with devastating simplicity, that the walk was impossible. For such a path to exist, every dot needs an even number of connections. Konigsberg has dots with 3 and 5 connections. Therefore, no such walk exists. Problem solved. But more importantly, a new kind of mathematics was born. What Euler had invented, almost by accident, was graph theory. The study of connections. Dots and lines. Nodes and edges. It sounds absurdly simple. And yet graph theory now underpins the internet, social networks, airline routes, neural networks, molecular biology, and the algorithm that decides which video you watch next. Every time Google Maps finds you the fastest route, it's solving a problem whose grammar Euler invented while thinking about bridges in a Prussian town that no longer exists. He wasn't solving a practical problem. He was solving a philosophical one. And the practical consequences took 2 centuries to arrive. But Konigsberg was just the warm-up. In 1734, 2 years before the bridges, Euler solved a problem that had defeated every mathematician in Europe for nearly a century. The baselproblem. What is the sum of 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, and so on, forever? The Bernoullis tried. Leibniz tried. Nobody could crack it. Euler showed the answer is pi squared over 6. Pi. In a sum of fractions. There are no circles anywhere in this problem. No geometry. No arcs. Just fractions stacked on top of each other. And yet pi appears, as if it had been hiding there all along, waiting for someone clever enough to find it. Euler was 27 years old. And this brings us to the equation that made Euler immortal. E to the power of I times pi, plus 1, equals 0. 5 numbers. 1 equation. E, the base of natural logarithms, born from compound interest and continuous growth. I, the square root of -1, an imaginary number invented to make algebra work. Pi, the ratio of a circle's circumference to its diameter, the most famous constant in all of mathematics. 1, the multiplicative identity. And 0, the additive identity, the number that means nothing and changes everything. These 5 constants come from completely different branches of mathematics. They have no obvious reason to know each other. And yet Euler showed they are bound together in a single, breathtakingly compact equation. Richard Feynman called it the most remarkable formula in mathematics. Benjamin Peirce called it absolutely paradoxical. The equation is beautiful not because it is complicated, but because it suggests that beneath the apparent chaos of mathematics there is a hidden unity. Something is connecting everything, and Euler found the thread. Euler didn't stop at analysis. He turned to geometry. Pick up any convex solid. A cube, a pyramid, a dodecahedron. Count the vertices, the edges, and the faces. Euler noticed something extraordinary. Vertices minus edges plus faces always equals 2. A cube has 8 vertices, 12 edges, 6 faces. 8 minus 12 plus 6 is 2. A tetrahedron has 4 vertices, 6 edges, 4 faces. For -6 plus 4 is 2. Every convex polyhedron in existence obeys this rule. V minus E plus F equals 2. This formula, now called Euler's polyhedron formula, became the foundation of topology, the study of shapes that can be stretched and bent but not torn or glued. One equation. An entire field. Again. Meanwhile, Euler was also reinventing number theory. He proved Fermat's little theorem rigorously. He discovered the law of quadratic reciprocity, though it took Gauss to nail the full proof. He introduced the totient function, which counts how many numbers less than n share no common factor with n. This function, phi of n, sounds like the most useless thing ever invented. Counting coprime numbers. Who could possibly need that? Everyone who has ever shopped online, that's who. RSA encryption, the security protocol behind every online transaction, every secure message, every time your bank verifies your identity, depends on Euler's phi function. He couldn't possibly have known. He was just counting numbers in 1750 because he found it interesting. Here is something that doesn't get enough attention. Euler invented the notation. The letter E for the base of the natural logarithm. Euler. The letter I for the imaginary unit. Euler. The sigma notation for summation. Euler. The function notation, f of x. Euler. Pi for the circle ratio wasn't his invention, but he's the one who made it standard by using it relentlessly in every paper he published. When you write mathematics today, you are writing in a language that Euler largely designed. He didn't just solve problems. He built the alphabet that everyone else would use to describe theirs. In 1766, Euler went completely blind. He had already lost vision in one eye 20 years earlier, after staring at the sun during astronomical observations. A botched cataract surgery took the other. Most people would retire. Euler's response to total blindness was to increase his output. He dictated papers to a scribe, holding enormous calculations in his head, visualizing entire proofs from memory. In the last 17 years of his life, blind and working from a chair, he produced nearly half of his total lifetime output. Roughly 800 papers. While completely blind. For context, most professional mathematicians publish fewer than 50 papers in an entire career. Euler wrote 800 without being able to see the page. Let's talk about the numbers. Euler published 866 papers in his lifetime. That is not a typo. 866. He wrote on mathematics, physics, astronomy, optics, music theory, naval architecture, and philosophy. When he died in 1783, there was such a backlog of unpublished work that the Journal of the St. Petersburg Academy continued printing his papers for 47 years after his death. Let that sink in. A dead man kept producing new mathematics for nearly half a century. The Collected Works Project, Opera Omnia, runs to over 70 volumes and still is not finished. There is a saying in mathematics, when you discover a theorem, check whether Euler proved it first. He usually did. Euler's work appears in analysis, algebra, number theory, graph theory, topology, mechanics, fluid dynamics, optics, and astronomy. There are Euler equations in fluid mechanics. Euler's method in differential equations. Euler's formula in complex analysis. Euler's formula in polyhedra. Euler's constant. Euler's line. Euler's circuit. The Euler-Lagrange equation. The Euler-Maclaurin formula. There are more things named after Euler than after any other mathematician in history. The closest competitor is Gauss, and even Gauss was standing on Euler's shoulders. Leonhard Euler looked at 7 bridges and saw graphs. He looked at fractions and found pi. He looked at 5 unrelated constants and found unity. He lost his sight and gained speed. And when he finally stopped, in 1783, the backlog of his genius took another half-century to process. Mathematics before Euler was a collection of separate rooms. After Euler, it was a building. Connected. Navigable. He didn't just contribute to mathematics. He gave it the words to describe itself. 4 fields. 800 papers. 1 man. And the bridges are still standing, mathematically speaking.